Let's explore nth roots. Let's do some examples to illustrate what is going on in general. What is the cube root of 64? Well, we want to find numbers, let's call them x, whose cube is 64. And this equation has exactly one real number solution, positive 4. That is what we mean by the cube root of 64. Let's make one change now. Let's do the cube root of negative 64. What we want here are solutions over the real numbers to the equation x cubed equals negative 64. And let's see. There's one number whose cube is negative 64, and it is negative 4. So that's what we mean by the cube root of negative 64. Let's continue. Let's go back to positive 64. Now let's take the square root. Let's do an even root. Solving this equation. This equation has two solutions, positive 8 and minus 8. Right? When you square negative 8, you get 64. And of course, when you square positive 8, you get 64. So this actually has two solutions. So now here, we don't want to define this expression as two different numbers, so we have to pick one. And what we will do is we will pick the positive root. We had a choice here, and we picked the positive root. Let's circle that. When you have a choice, use the positive root. Finally, let's take the even root of a negative number. This is like solving the equation x squared equals minus 64. Solving this over the real numbers. And this has no solution. So, square root of negative 64 does not exist over the real numbers. Let's summarize what we saw at the end with those last two examples. That was dealing with the square root in those examples, but generally, whenever you're taking an even root of a number, you have the following two possibilities. When the radicand, the number under the radical sign, is positive, we saw that the nth root does exist, and it is positive. And when the radicand is negative, the nth root does not exist. This is, again, it emphasizes, as a real number. It does exist as an imaginary number, but not a real number. Let's do problem 20 out of our point 8. Simplify this radical expression. So simplify here means when we take the radicand, we can simplify whenever we have a perfect square factor. So we want to write this as, we want to factor it as a product of perfect squares times a factor that has no perfect square in it. And here we see that 9x to the 5 has, let's deal with the perfect squares. What perfect squares divide 9x to the 5? One is 9 itself. Another is x to the 4. And what remains is x, which has no perfect square factor in it. So we've accomplished our goal. Let's see how we can simplify this radical expression using that. We'll go through the steps. We said 9 was a perfect square. We said x to the 4th was a perfect square. And of course we have x left over. So the square root of 9 is positive 3. The square root of x to the 4 is x squared. And the square root of x cannot be simplified. So our final answer, put it in the box here, 3x squared times the square root of x. Let's do another example. Let's rationalize a denominator in this expression. Let's rationalize the denominator. What does rationalize mean? We have to ask ourselves that first. It means simply to eliminate all radicals. So our goal is, we don't just simply remove the radical over 7. We need to take this quotient, find an expression equivalent to it, equal to it, but with no radical in the denominator. It needs to be equal to. Let's see what we can multiply the denominator by to eliminate the radical. Let's just focus on doing that. Well, if we remember that a binomial times its conjugate, a plus b times a minus b, is simply a squared, the square of the first term, minus b squared, the square of the second term, we can use that here. Let's see what happens. This is, again, the conjugate. That's the word conjugate. What happens when we multiply by the conjugate? We said it's the square of the first term, square root of 7 squared, minus the square of the second term, 2 squared. So this will equal 7 minus 4, which is 3. Good. So we multiply the denominator by square root of 7 minus 2. We will have eliminated the radical. We will rationalize the denominator. Eliminated the radical in the denominator. So now we have to remember that this is our original expression. And since we need to find an expression equal to it, we can only multiply the expression by 1. So we would need to multiply it by the square root of 7 minus 2 over the square root of 7 minus 2, right? This whole thing is equal to 1. Multiplying by 1 in this special shape. Let's see what the new numerator is. We would have the square root of 14 minus 2 root 2. And this would be our final answer. Now you see that there are radicals in the numerator. That's okay. What they want is no radical in the denominator. So this is good.